Good afternoon, everyone. Today's lecture is going to focus on the Devonian period, was from 419 to 359 million. Devonian is interesting for a number of reasons. One is because we start to see more large-scale invasion of plant life on land. Then coupled with that, we see the first animals step foot on land, and one of those major revolutions biology. Once animals invade the land, of course, they were our ancestors. They led ultimately to the colonization of land and the development of land. The name Devonian itself comes from Devonshire, Cornwall, and Devonshire in the UK, and it was introduced in 1829 by Merchant Sedgwick to describe these older rocks. And it was nicknamed this kind of a nickname, the Old Red Continent, because if you recall from last lecture, the Acadian orogeny had started, and that was the collision of Europe with North America. And when that happened, of course, the ocean closed, and we began to see more continental type sediments, siliclastic sediments, silica-rich, quartz-rich sediments were typically red in color, hematite-rich. And so this continent of Euro-America was nicknamed the Old Red Continent because of this abundance of red sandstone. It's also famous, among other things, it's nicknamed the Age of Fishes because fish became very abundant in the ocean and dominate sea life. So several things going on in the Devonian court. If you recall this, it showed these transgressive, regressive sequences, and I forgot to mention this, but when we talked about the Ordovician, the tectonic orogeny, you can see that during these orogenic events, there tends to be a transgression, and then as the mountains build, elevate the land, and you get regression. So here we have the Antler and Acadian orogeny west. You can see we get a regression here during the Devonian, then after this Kaskaskia transgression. So in terms of sea level, during the Devonian, sea level was quite high at the end of the Silurian into the early Devonian. Then by the late Devonian, sea levels began to drop, in part because of the Acadian orogeny. As we see in the next, we're getting very close to Pangea, so large. The Old Red Sandstone is, again, this famous. This is an outcrop in Scotland of the typical Old Red Sandstone, and you can see here that Old Red Sandstone is folded. These rocks have been deformed, and these rocks were deformed during the collision of Europe with North. So this is where it gets its name. You can see these. If you look around, even around the eastern coast of North America, and you find Devonian features. Very typically, there'll be this bright red color. In terms of major Devonian events, we have the conclusion of the Acadian orogeny. The Acadian started in the Silurian. It is completed in the Devonian. In terms of evolution, we see the rise of fish. Fish were around before then, but they really became dominant in the ocean. We see the rise of tetrapods. These are terrestrial animals. These are the forerunners of humans, so our early ancestors. We begin to see trees and forests appear on land. So this entire terrestrial ecosystem really takes hold in the Devonian. The Devonian climate was equable, with many of the continents situated on the equator, but there were strong zonal climates as well. What does that mean? That just means the Devonian climate was typical to what we see today. So we have climatic zones on Earth today. Devonian climatic zones are probably similar. The Frasnian Femmenian, there are two extinctions of the Devonian. The first is called the Frasnian Femmenian extinction. The Frasnian and Femmenian are two stages in the Devonian. So we have periods be further divided up into stages, and in the late Devonian, this Frasnian Femmenian boundary there was a large extinction. It's called the Kellwasser. And then at the end of the Devonian, there was also a mass extinction. These are very close in time. They take place within 20 million years of one another. And it's unclear if the Frasnian Fomenian began the extinction, continued to run to the end of Devonian, or whether these were pulse extinctions, one Frasnian and one at Devonian. In either case, this end Devonian mass extinction is one of the big five extinctions on Earth. It wiped out about 80% of marine organisms and 50 to 60% of terrestrial organisms. This is a big extinction. Again, we talk about some of the big five: Ordovician, the Devonian, the Permo-Carboniferous, the Cretaceous, of course, today. We'll go a little bit later in the course after we talk about all of these big five extinctions, kind of go and take a step back and say, okay, what do they have in common and what is different about each one of these things? But nevertheless, this end Devonian extinction is one of the big five extinctions of life on Earth. I mentioned evolution, the rise of fishes, the start of tetrapods, the invasion of land animals, beginning of forests and land. And Devonian life is really a hallmark step in evolution. It's important to remember this. I talked earlier in the course about singularities, about the first living organism, the first prokaryote, the first eukaryote, the first metazoan, the rise of oxygen on Earth. The Devonian, you could make the argument that the Devonian is another one of the singularities in Earth history, where we had this rich marine ecosystem up until this point, and then suddenly the terrestrial ecosystem just exploded. And because we are terrestrial animals, we should consider that this was actually an important evolutionary. So let's talk about this from fish to land, because it's an interesting story. And if you start thinking about it, we will think about it, it's not an easy thing to do. It's not an easy transition for an organism to go from living in an aquatic environment and then moving into a uniquely terrestrial environment. And this happens pretty quick in the Devonian. And we can see some evidence of this. This is a tetrapod trackway that's found in Kentucky. Now you make it out, see these little footprints here in the sandstone. And so we see these, if you think about it, we have fish, and these fish have to learn to live on land, or they have to develop tools and the biology to live on land. If we look at the fishes, we won't go through all the fishes. There's tons of them in the Devonian. We're going to look at my favorite one, which is Dunkleosteus. This is probably the terror of the ocean, the great white shark of the Devonian. And you can see it's pretty fierce looking. It had an armored skeleton. It was probably, I would say up to 12 to 15 feet in length, and it terrorized the ocean. Here is a fossil of Dunkleosteus. So you can see it was an armored fish. It had not only these big teeth, but it had this big skeleton. And when you're king of the ocean, of course, you eat pretty much anything you want. Dunkleosteus were great hunters. There is even evidence that they were cannibals. Right? They ate each other as well. So this was the king of the Devonian Ocean, similar to what we great shark. But in the Devonian, the big thing, one of the great moments of the Devonian was the transition from aquatic to terrestrial life. And this is an old far side chart. How did fish move from water to land? Thinking about this for just a minute, living in water is unique. It's a unique adaptation, but the transition from living in an aquatic environment to a terrestrial environment means that half the organisms make that transition have to have biological revolutions change their mechanism of reproduction. So think about it, in the water, a lot of aquatic animals either lay their eggs within the water, or you know, in terms of fish, they have their eggs in them and they release the eggs. Everything's done in an aquatic environment. When you move on to land, suddenly you have stressors on land, right? Because now you can't just lay the egg on the surface of the land because they're exposed to all the stuff that can damage eggs in the terrestrial environment. They can desiccate, they can be bombarded with UV radiation, they can be eaten by others. Of course, that can happen in the aquatic environment as well. But the terrestrial environment presents more hurdles to reproduction. So whatever organisms occupy land, they have to change their reproductive strategy. This will, of course, continue on evolution, lizards and mammals and so forth. So reproductive changes have to occur at the same time as invasion of land. Movement. If you've gone swimming in water, you know that swimming supports. You have a buoyancy, and you don't feel as heavy in the water as you do in land. So just moving in the water and moving on land have very different physical demands, right? If you're in the water, you can swim, maybe crawling on the ocean floor, that's fine. But you move differently in water than you do on land. So there's different physical demands. There's different framework structures, different bone structures that are needed. There are different, motions have to be synchronized differently on land than in water. Swimming is very different from walking. A big one is respiration, right? If you're living in an aquatic environment, fish are able to get their oxygen from the water, but you have to change, right? Because now there's no water to get the oxygen. You have to draw the oxygen out of the air. So different breathing mechanisms, different lung setups, and then feeding, new sources of food, right? If you're a marine organism, you can go to the reef. There's lots of food there. If you're living on land, you have to have new sources of food, probably new digestive enzymes, new digestive processes. So if you just think, oh, well, they just had to move out of the water onto land, everything was hunky-dory, it's actually much harder than that. There's a lot of changes that had to take place over a relatively short amount of time. Because the Devonian, we're really talking about 60 million years, and in that 60 million years, we see this rapid transition from life in the ocean to life on land. So if you were walking around in Silurian, there were Silurian plants. There were probably not many organisms around on land during the Silurian. If you then woke up in the middle of the Devonian, suddenly you would forests with animals moving around. It would just be a drastic transition. And so from an evolutionary perspective, this had to be one of those leaps forward in evolution biology. So keep that in mind. If we look at this in terms of, okay, what did the first land walkers look like? And the tetrapods seem to be the first invaders of land. And so we have this evolutionary tree here, starting with what were pretty much fishes. They're all different types of fishes in the Devonian. And then we start seeing these lobe-finned fishes. And it's these lobes, in particular these frontal and back lobes, that will develop and will evolve from lobe-finned fish into legs. So this is a evolutionary chain. What's cool about this is that we are able to figure out what these intermediates look like. So kind of the first lobe-fin fishes appear here. They were around in early Devonian. Um, they evolved into a little bit longer lobe, a little bit different head structure in Panderichthys. And then we get these fish here that are the true transitionals. And the first one is Tiktaalik rosier, and this was discovered, a partial fossil discovered in Greenland earlier in the 2000s. And then I sent you this discovery that was made just last week called E. watsoni. It is another intermediate. It is in this same evolutionary stage as Tiktaalik. It looks very similar to Tiktaalik, except the fossil is much more complete, much better preserved. So we really get a good view into the evolution of and the transition from these fish into terrestrial organisms. So if you think about this, and there's a book called My Inner Fish by the discoverer of Tiktaalik rosier, these are our ancestors. These are our evolutionary ancestors, and this transition from marine terrestrial is a big leap forward. And then after Tiktaalik and E. watsoni, we begin to see the first really tetrapod, which is Anthostega, and then Ichthyostega. So this is the transition from these lobe-fin fish to terrestrial organisms. So the fish that are related to the tetrapods, these lobe-fin fish here, you can see this kind of a schematic of what they look like. But these are the four limbs or the four lobes, and these are the back lobes. So these will develop into the front leg and the hind leg in tetrapods. Here is Panderichthys. Go back to that evolutionary chain here. So we're going from this to Panderichthys here. And you can see that these lobes have now extended. They're much longer. They're beginning to resemble limbs. They're more like legs, hind legs, forelegs. And notice that the head is changing as well. So one of the things that has to change as you move from aquatic terrestrial life is that your head structure has to change as well. So we begin to see this transition. Right? Then we get to the intermediates, and this is what's fun, because in evolutionary biology, right, we're dealing with a fossil record. And so we know that there were tetrapods. Tetrapods have been known from the fossil record for a long time. It's first organisms living on land, and they had legs. They had hind legs, they had forelegs. We know these lobe-finned fishes. They've been in the fossil record. We've known about them for a long time. They don't have legs. They have fins. They have fins that look like legs. They're long. They're different than a lot of other fish. But we don't have this transition from true fish to true tetrapods. And we want to see the evolution of the lobe-finned fish to the first hind feet and forefeet. So the fossil, the first discovery was discovered in Greenland. I can't remember, 2002. And it actually is a transitional fossil from a true fish to a true tetrapod. It is the transition to land dweller. It's called Tiktaalik rosier. And then last week, there was a second discovery made called E. watsoni. It is also an intermediate and belongs to this intermediate. So what did they look like? Well, here's Tiktaalik. Again, you can see it's incomplete. Pretty good head preservation. The rest of the body, not so much. But here you can see this four-limb development, Tiktaalik rosier, much better preserved in E. watsoni. I'll show you. So this was the first intermediate. And these two fossils Tiktaalik and E. watsoni. In terms of timeline in this evolutionary process, they were roughly about the same age, about 385. Well, here's E. watsoni, and you can see that E. watsoni has these fin feet, yeah, almost identical. And if I here, bear with it, I'm going to stop the slideshow for just a second. Hang with me. I'm going to blow up that image so that you see. This will just show. Okay, here we go. So this is E. watsoni here, and you can see they did a CT scan of the fin bones, same scale as shown on the left. And so this is the fish, this E. watsoni, and this is a tetrapod, and you can see the similarities in terms of the structure. Both have a very similar shape humerus, both have a radius ulna. The difference here is that this has the second ulna or ulnare, whereas tetrapods have carpal bone digits, but we also see those same digits here in watsoni. So this is a really cool transitional fossil showing us how we went from lobe fin fish, from lobe to feet. Then we get to the first true tetrapod, this Acanthostega. It probably easily between aquatic and terrestrial environment. More than likely, the tetrapods, in terms of their reproduction, probably still laid eggs in the aquatic environment. So this was an animal that was happy in both places, both aquatic and terrestrial environment, but it was adapted to live on the land. So Acanthostega go on land. And then the first really land-dwelling tetrapod, Acanthostega here, and you can see the fully developed kind of. So that's a major accomplishment in evolution. You can see the timeline, about 380 million years ago to about 360 million years ago. So in that 20 million year interval, we go from these lobe fin fish with fins that look like this, to fins with a wrist and Tiktaalik, and then to normal limbs, things like Acanthostega, and E. watsoni would fit right in here with Tiktaalik, somewhere down in the center. So it was a true transitional, much better preserved Tiktaalik rose it was. Gives us some insight into the evolution of limb in the tetrapod. Plant life in the Devonian. Originally, plant life in the Devonian was thought to be somewhat simple. There were trees, but they were thought to be more primitive trees. Here's Archaeopteris as opposed to Archaeopteryx, the bird. This is Archaeopteris, an early land plant. Cooksonia, fairly simple plant. But there was a new discovery made in 2019 up in New York, and they found big trees. So you can see this is a tree root system, or fossil tree roots extending out the human scale. So these must have been fairly sizable trees. And not only that, they were modern type trees. And by modern type trees, I don't mean indigenous trees, but they had root systems. They must have been sizable. They were community trees, so they found root traces, trunk trace trees in groups within the Devonian. So this seems to indicate that there were well-established forest systems formed during the Devonian. It's very different than what we thought 10 years ago. We thought that forest or that land terrestrial ecosystem in terms of plants a little bit simpler in the Devonian, about that they are likely much more complex. If we move on to the tectonics of the Devonian, we are beginning to see we are seeing the final phases of Akkadian orogeny, so the formation of Euramerica or Laurasia or Laurussia, or basically North America and Europe, along with Siberia, are combined into this northern continent. So remember from your early class, you had the supercontinent of Pangaea and this northern continent called Laurasia and the southern continent of Gondwana, and they collided in short time. They collided in the Permo-Carboniferous after. So we're beginning to see the destruction of this ocean between Euramerica and Gondwana, and the formation of Euramerica, which marks the formation of this northern landmass, takes place or ends, begins in the Silurian and ends during the Devonian. So we're witnessing the other half. Remember, Gondwana formed in the Cambrian, and Euramerica is forming the Devonian. So we got those two pieces that are going to come together. Pangaea. We can look at the globe again. These are the typical two views of the globe that I show you. Here is Euramerica. This is Gondwana. So you can see that the ocean between Euramerica and Gondwana is quite small and almost have a supercontinent here in early Devonian. By 400 years, we have Gondwana here, separated by a small ocean from Euramerica, old red continent. So we're nearly Pangaea, but not quite. Just finished the formation. The extinctions, there are two. I mentioned this, two or one protracted extinction. The first is the Frasnian Flammenian, the Kellwasser event. Kellwasser is the location in Germany where this is well documented, about 375 million years. And then the End-Devonian Hagenberg extinction, about 359 years. It's about 16 to 20 million years between these two, or a protracted extinction over 20 years in the late Devonian. The Frasnian Flammenian extinction affected both marine and terrestrial ecosystems. If you look at the diversity of marine invertebrates, land plants, spores, and macroflora, you see this decrease in the diversity across the Frasnian Flammenian. And then when you couple that to the Hagenberg extinction, where you wipe out 80% of marine animals and up to 60% of land animals, this is one of those big five extinctions in Earth history. Now, what caused this? The Frasnian Flammenian is a bit troubling. It's really hard because we have these coupled events. One which the Frasnian Flammenian really hits marine ecosystems harder. The Hagenberg seems to hit terrestrial organisms harder. And it's unclear as to whether this is the long continuum of an extinction event, in which case we have to look for something that we have to look for a cause of this extinction over 20 million years. If they are short duration events, if there was two distinct events, Kellwasser and Hagenberg, then we can maybe look for something more diabolic, like a asteroid collision, something like that. So it depends on whether these extinctions are protracted or distinct. But there's been a variety of causes to explain this, including climate change, and there are arguments that it was either got cooler or it got warmer, take your pick. An increased influx of terrigenous sediments to continental shelf caused by the appearance and spread of deeply rooted forest ecosystems. So think about that. So remember, we've got this ocean closing up. We have Euramerica forming. Well, Euramerica formed because oceans closed between Euramerica. So we're beginning to lose shallow marine environments. That makes sense, right? we're closing oceans, we're losing that environment. We're also uplifting. So as continents uplift, they begin to erode, and then you can see erosion into the surrounding ocean dirtier. And it may be that combined with sediments that included terrestrial processes, so forest ecosystems eroding out their chemicals into the ocean. It may have been some combination of that. If you move to the more bizarre, there are people who propose gamma ray bursts, nearby supernova explosions. There have been asteroid impact explanations for this. And we even suggested that looking at present paleomagnetic record, that there may have been a second magnetic field hyperactive reversal episode during the time interval, which would have weakened the magnetic field. Same sorts of things that we saw in the Ediacaran extinction, except this would also affect organisms. It's unclear. It's unclear what caused these extinctions. There's lots of arguments about what caused these extinctions. But what we do know is that this was one of the big five extinctions. Okay, we're going to stop there. In the next day or so, I will go through the Carboniferous and Permian. We'll finish up the Paleozoic in the next couple of days. Some accounting. You should have received the homework assignment that is due, I believe, the end of this month. And it is kind of a fossil, and then there's questions associated with that. Do your best. I think I also mentioned about a short video about taking this course SU versus grade. There's been a lot of confusion about that. So let me tell you what I know right now. You can take this course SU. S is defined as a C grade. So if you're taking this course SU, you have to get at least C. I don't see that being a problem for anybody in the class so far. Just do the next two assignments, which make up the second test, and then I'll have a couple more assignments that will make up your third test, and then Scott is working on the labs, trying to get those. So just do your best. I really think that in the end, if you do put forth a good effort on it, I don't see a problem. There's a real point. Take S grade over a letter grade. S grade does not figure into your GPA, so that. But you can always either email me, give me my phone, text me, right? All right, so I'm going to stop there, and we'll